Let me take you on a journey tonight, a gentle drift through time and space, back to the very beginning of everything you know. Close your eyes if you wish, and let yourself float with me through the cosmos, where we will discover together how the smallest particles of dust became worlds, became oceans, became you. Tonight, we are not rushing anywhere. There is nowhere to be but here, drifting softly through the story of creation itself. Every breath you take connects you to this ancient tale, and as we move through it together, you can let go of everything else, allowing the vastness of space and time to hold you. The ancient cloud where everything began. Imagine, if you will, a place of absolute stillness. Not the stillness of an empty room, but the profound quiet of space itself, stretching out in every direction without end. This is where our story begins, not 5 years ago or 500 years ago, but 4.5 billion years in the past, in a region of our galaxy that would one day become our neighborhood, though nothing remotely familiar existed there yet. There was a cloud floating in this darkness, a cloud so vast that your mind cannot truly hold its size, but we can feel it together. This cloud stretched across distances of trillions upon trillions of miles, a collection of gas and dust suspended in the nothing, lit only by the distant light of stars far away. If you could have floated there in that ancient time, you would have seen a faint glow, a soft luminescence like the earliest light of dawn, except this dawn had been glowing for millions of years and would glow for millions more. The cloud was not uniform, not a simple mist spread evenly through space. No, it had texture, dimension, personality. In some regions, the dust and gas gathered more thickly, creating darker patches against the already dark sky. In other areas, the material spread thin, almost invisible, just the faintest whisper of matter floating in the void. The dust particles themselves were unimaginably small, each one measuring less than 1,000th of a millimeter across, smaller than anything you could see with your naked eye, smaller than a single bacterium, smaller than a speck of pollen drifting on a spring breeze. These dust grains were not made of anything exotic or strange. They were made of the same elements that make up everything in your world today. There was carbon, the same carbon that forms the graphite in pencils and the diamonds hidden deep in the earth. There were tiny crystals of silicate minerals, relatives of the sand on beaches and the glass in windows. There were iron particles, microscopic versions of the metal that would one day form the cores of planets and the steel in buildings. There were ice particles too, frozen water and frozen carbon dioxide and frozen methane, each tiny crystal catching and reflecting the distant starlight. The cloud had been there for so long, just existing, just being. Nothing dramatic was happening. The particles drifted past each other in the silence, moving so slowly that you would not perceive their motion even if you watched for years. Some particles had been floating alone for 10 million years, never coming close enough to another particle to interact. Some had been part of the cloud since its formation, while others had been captured from passing stellar winds, gifts from other dying stars. This cloud, our ancient ancestor, was cold beyond imagining. The temperature hovered just a few dozen degrees above absolute zero, that theoretical point where all motion ceases. In this cold, everything moved in slow motion, every vibration dampened, every particle conserving what little energy it possessed. There was no warmth here, no fire, no heat. Just cold dust and cold gas, drifting together in the dark. The gas was mostly hydrogen, the simplest element, the most abundant substance in the universe. Hydrogen atoms floated between the dust particles like an invisible ocean, each atom separated from its neighbors by distances vast compared to its own size. Mixed with the hydrogen was helium, the second element, also simple, also abundant. These gases had existed since the very beginning of the universe itself, created in the first moments after the Big Bang, and they had been drifting through space for more than 9 billion years by the time our story begins. But something was about to change, though so slowly that you would not notice it happening. Somewhere, perhaps many light years away, a massive star was ending its life. This star had burned brilliantly for millions of years, fusing hydrogen into helium, helium into carbon, carbon into heavier elements, building up a periodic table inside its core. Now, having exhausted its fuel, the star was collapsing, and in that collapse, it would explode, sending a shockwave racing through space at thousands of miles per second. This shockwave was coming toward our cloud, though it would take thousands of years to arrive. When it did arrive, it would compress the cloud, pushing the dust and gas together, creating ripples and waves through the material. This compression would be gentle at first, barely noticeable, just a slight increase in density here, a small gathering there. But compression leads to more compression, and gathering leads to more gathering, and once the process begins, it continues, slowly and inevitably, like water finding its way downhill. The cloud began to collapse. Not everywhere at once, but in certain regions where the dust and gas had already gathered slightly more thickly. In these regions, gravity, that patient and persistent force, began to pull particles together. Gravity is so weak when you are dealing with tiny particles, so subtle that it can barely be measured, but it is always there, always pulling, never resting. Given enough time, given enough material, gravity always wins. As the cloud collapsed, it began to spin. This spin was not something new, but something that had always been there, just imperceptible before. Every particle in the cloud had some tiny motion, some small velocity in some direction, and when you add up all these tiny motions across trillions upon trillions of particles, a pattern emerges. The pattern is rotation, a slow turning like a whirlpool forming in water as it drains. The cloud spun slowly, taking thousands of years to complete a single rotation, but as it collapsed and grew denser, the spin accelerated. This is the same principle that makes ice skaters spin faster when they pull their arms in close to their body. As the material moved inward, closer to the center, it had to move faster to conserve angular momentum, that fundamental property of rotating systems that cannot be created or destroyed. At the center of the collapsing cloud, where the dust and gas gathered most densely, something new was beginning to form. The pressure was building there, particle crowding against particle, and with pressure came heat. For the first time in this story, warmth entered the picture, though warmth is perhaps too strong a word. The temperature at the center began to rise, degree by degree, century by century, from the incredible cold of the outer cloud towards something less hostile to existence. This central region would become the sun, though it was not a sun yet. It was just a growing ball of gas and dust, glowing dimly from the heat of compression, not yet hot enough to ignite the fusion reactions that would make it a true star. Around this protosun, the remaining material of the cloud began to flatten into a disk, pulled by the spin of the system into a wide, thin plane that extended billions of miles in all directions. This disk was still mostly gas, still mostly hydrogen and helium, but the dust particles were there too, now gathered more closely together than they had been in the original cloud. These dust particles were the seeds of everything solid that would ever exist in the solar system. They were the beginning of planets, the beginning of moons, the beginning of asteroids and comets, the beginning of Earth, the beginning of you. The disk glowed with a soft, reddish light, illuminated by the protosun at its center and by its own gentle warmth. If you could have seen it from above, from outside the plane of the disk, it would have looked like a vast wheel of light turning slowly in the darkness, beautiful beyond description, peaceful beyond measure. This was the solar nebula, the birthplace of our solar system, and it hung there in space, evolving, changing, preparing for the next chapter of creation. Time passed. Not hours or days, but thousands and thousands of years. The disk continued to exist, the protosun continued to grow, and throughout the disk, the dust particles continued their slow dance, moving through the gas, occasionally bumping into each other, occasionally sticking together. These collisions were the beginning of something profound, though they seemed insignificant at the time. Just tiny particles touching, adhering, becoming slightly less tiny. But every journey of 1,000 miles begins with a single step, and every planet begins with a single grain of dust finding another. When dust particles first found each other. In the disk that surrounded the young protosun, the dust particles were everywhere, mixed thoroughly with the gas that dominated the nebula. Each particle drifted along its own path, following an orbit around the center, pulled by the gravity of the growing sun. These orbits were not perfect circles but gentle ellipses, and each particle moved at a slightly different speed, following a slightly different path, so that occasionally, inevitably, particles would pass close to one another. When two dust particles came very near, separated by just a tiny fraction of a millimeter, strange and wonderful forces began to act between them. These were not the forces you experience in your daily life, not the friction of solid objects or the push and pull of magnets. These were molecular forces, the subtle attractions between atoms, forces called van der Waals forces by scientists, though the name matters less than what they did. These molecular forces reached out from each particle like invisible fingers, feeling for the other particle, and when the particles came close enough, these forces would grab hold and pull them together. The particles would touch, their surfaces meeting, and in that moment of contact, they would stick. Not always, not every time, but often enough. Often enough that over thousands of years, over millions of collisions, the dust began to gather itself together. Imagine two particles that have just stuck together. They are now slightly larger than either was alone, perhaps twice the size, though still far too small to see with your eye. This new combined particle continues to drift through the disk, following an orbit that is some combination of the orbits of its two component parts. As it drifts, it will encounter other particles, and sometimes it will stick to them too, growing larger still. The process feeds on itself. Larger particles have more surface area, which means more opportunity to stick to other particles. They also have slightly more gravity than single dust grains, and while this gravity is weak, it is there, adding its gentle pull to the molecular forces. As particles grew from 2 grains to 10 grains to 100 grains, they became more efficient at collecting additional material, sweeping up dust from their surroundings like cosmic vacuum cleaners. The first particles to reach the size of sand grains, about 1 millimeter across, crossed an important threshold. At this size, they began to settle toward the midplane of the disk, the central thin layer where the disk was most dense. Gravity pulled them downward, out of the thicker gas above and below, concentrating them into an even thinner layer where encounters between particles became more frequent. This settling happened slowly, each particle drifting downward like a feather falling through honey, taking thousands of years to complete its journey. In the midplane, the conditions were perfect for growth. The dust was concentrated there, packed closely together compared to the rest of the disk. Collisions became frequent. A particle that had taken 10,000 years to grow to the size of a sand grain might grow to the size of a pebble in just another 1,000 years. The pace was accelerating, though it would still seem impossibly slow to you watching it happen. Not all particles grew at the same rate. Some found themselves in regions of the disk where dust was more abundant, and they grew quickly, becoming the lucky ones, the seeds of future worlds. Others drifted in regions where dust was sparse, and they grew slowly, remaining small, perhaps eventually joining larger particles as they passed by. And some particles, through the randomness of their orbits, were thrown out of the disk entirely, ejected into interstellar space, their chance at being part of a planet lost forever. The temperature of the disk varied with distance from the protosun. Close to the center, where the heat from the collapsing gas was strongest, temperatures climbed above the boiling point of water. Here, only particles made of rock and metal could survive as solids. Particles made of ice would evaporate, their water turning to vapor, their carbon dioxide sublimating away. These volatile materials would be carried outward by the gas, away from the heat, toward the cooler outer regions of the disk. Further out, beyond a distance of about 300 million miles from the protosun, temperatures dropped below the freezing point of water. Here, ice particles could survive and even form, as water vapor from the inner disk condensed back into solid crystals. This boundary, called the frost line, was an invisible division that would have profound consequences for the kinds of worlds that formed on each side of it. Inside the frost line, planets would form from rock and metal alone, becoming the small, dense, terrestrial worlds. Outside the frost line, planets could incorporate vast amounts of ice along with rock and metal, and these planets would grow much larger, becoming the giant worlds of the outer solar system. But all of this was still in the future. For now, there was just dust, growing grain by grain, pebble by pebble. The pebbles continued to grow, reaching the size of your fist, then the size of your head, then larger still. At these sizes, the objects were no longer held together just by molecular forces but by their own weak gravity, each particle pulling on its neighbors, the whole mass holding itself in a loose embrace. These small bodies, now perhaps a few feet across, are called planetesimals by scientists, the first solid objects in the solar system that truly deserved their own name. The formation of planetesimals was a critical step, a tipping point in the process of planet formation. Once objects reached this size, their growth could accelerate dramatically because their gravity, while still weak, was strong enough to pull in material from a distance rather than relying on chance collisions. A planetesimal drifting through the disk would gravitationally attract nearby dust and pebbles, pulling them in, accreting them onto its surface. The larger it grew, the stronger its gravity became, and the faster it could gather material. Within the disk, thousands, perhaps millions of planetesimals formed, scattered throughout the region that would become the solar system. They ranged in size from the smallest ones, just a few feet across, to the largest ones, which grew to dozens of miles in diameter. These bodies orbited the protosun independently, each following its own path, each slowly growing as it swept up material from its vicinity. But the disk was also a chaotic place. Orbits crossed and intersected. Planetesimals that had formed in slightly different locations, moving at slightly different speeds, would sometimes encounter each other. When two planetesimals met, several things could happen, depending on the speed and angle of their collision. If they met gently, at low relative velocity, they might stick together, merging into a single larger body. The collision would be soft, almost tender, the two bodies kissing and embracing, their mutual gravity pulling them together, their surfaces interlocking. This was the path toward building planets, the process of accretion continuing at a larger scale. But if they met with too much speed, the collision could be destructive. The impact would shatter one or both planetesimals, breaking them back down into fragments, undoing thousands of years of patient growth in a single violent moment. These fragments would then drift separately through the disk, eventually joining other planetesimals or slowly reaccumulating into new bodies. Most collisions fell somewhere between these extremes, neither perfectly gentle nor catastrophically violent. A collision might chip pieces off one or both planetesimals while still allowing the main bodies to stick together. Or it might cause the larger body to capture the smaller one as a satellite, the two objects orbiting each other as a binary pair for a while before eventually merging. Through this process of collision and accretion, certain planetesimals began to dominate their regions of the disk. These were the lucky ones, the ones that had grown large enough and fast enough to begin clearing out their orbital zones, gravitationally shepherding smaller bodies toward them. These dominant planetesimals, the largest ones, would continue growing at the expense of their neighbors, becoming the embryos of planets. The dance of the planetesimals continued for millions of years, a slow-motion ballet of rock and ice, of collision and merger, of growth and occasional destruction. The disk was gradually transforming from a relatively smooth distribution of dust and gas into a system of discrete bodies, solid objects with defined boundaries and individual identities. The process was messy, chaotic, unpredictable in its details, but guided by the universal laws of physics toward an inevitable outcome. And at the center of it all, the protosun continued to grow and compress, its core temperature rising as more and more material fell inward. Eventually, inevitably, the temperature and pressure at the core would reach the critical threshold where hydrogen atoms would begin to fuse into helium, releasing tremendous energy. When that moment arrived, the sun would truly be born, a new star igniting in the darkness, flooding the disk with light and heat and powerful stellar winds that would change everything once again. The quiet birth of solid ground. As millions of years passed in the disk around the young sun, the planetesimals continued their slow but inexorable process of gathering together. In the inner regions of the solar system, inside the frost line where temperatures remained high and only rock and metal could exist as solids, a particular story was unfolding. Here, for distinct regions were clearing themselves of material, for areas where the largest planetesimals had become so dominant that they were well on their way to becoming planets. The process of going from planetesimals a few miles wide to planets thousands of miles wide required time and patience. A single planetesimal, even a large one perhaps 60 miles across, does not have very strong gravity. If you stood on its surface, you could easily jump into space and drift away. Its pull on nearby objects is gentle, persistent, but not overwhelming. Growth at this stage happens slowly, as the planetesimal's weak gravity gradually pulled in smaller bodies from its vicinity. But gravity has a property that makes it special among forces. It always attracts, never repels. Every particle of matter in the universe attracts every other particle of matter, and while the force is weak when objects are small or far apart, it never goes away, never reverses. It just keeps pulling, forever, patient as eternity itself. And as an object grows, its gravity strengthens, which allows it to pull in more material, which makes it grow more, which strengthens its gravity further. This is what scientists call a positive feedback loop, and it is the engine that drives the formation of planets. In the region closest to the Sun, where the disk was hottest and most of the material had been blown away by the intense radiation and stellar wind, a small rocky world was slowly taking shape. This would become Mercury, the smallest of the terrestrial planets, a world that would eventually end up with a huge iron core and a relatively thin rocky mantle. The planetesimals here were moving fast, whipped around the Sun at high speed by the strong gravitational pull of our star, and collisions between them were often energetic, sometimes destructive, but gradually one body emerged as the dominant mass. Further out, in a cooler region where more material had survived, another rocky world was forming. This would become Venus, similar in many ways to the planet that would form beyond it but with its own distinct character. The planetesimals in this region collided and merged over millions of years, each impact adding mass, adding heat, adding momentum. The growing planet's surface was not solid in the way we think of solid ground today. It was hot, molten in places, a churning mass of semi-liquid rock constantly reshaped by impacts and by the slow convection currents that carried heat from the interior to the surface. Beyond Venus, in what scientists call the habitable zone, a region where temperatures were moderate and water could exist as a liquid, the most important world for our story was beginning to form. This was the proto-Earth, the early version of the planet you are standing on now, though it looked nothing like the Earth you know. It was growing through the same process as all the other terrestrial worlds, collision by collision, merger by merger, each impact contributing more mass to the growing planet. Each collision between the proto-Earth and a planetesimal was a moment of transformation. When a planetesimal perhaps 10 or 20 miles across struck the growing planet, it would hit with tremendous energy. The speed of impact might be 10 miles per second or more, and at such speeds, the kinetic energy of motion converts instantly into heat. The impact would create a crater, vaporizing both the incoming planetesimal and a portion of the planet's surface, throwing molten rock high into space, generating shockwaves that rippled through the entire body of the planet. These impacts kept the surface of the growing Earth hot, molten, glowing with the heat of formation. There was no solid ground yet, no crust, no continents, no oceans. Just a ball of hot rock, growing larger with each passing million years, its surface constantly reshaped by impacts large and small. The heat from the impacts, combined with the heat released by radioactive decay of elements like uranium and thorium in the planet's interior, kept the entire body molten enough for heavier materials to sink and lighter materials to rise. This process, called differentiation, was crucial to creating the layered structure that Earth has today. Iron and nickel, being denser than the silicate rocks that made up most of the planet's mass, began to sink toward the center, pulled by gravity through the semi-molten rock. Over millions of years, this created Earth's iron core, a sphere of metal at the planet's heart, surrounded by a mantle of lighter rocky material. This is why Earth has a magnetic field today, because the liquid outer core, still churning and convecting, generates electrical currents that produce magnetism. Still further from the Sun, beyond Earth, another terrestrial world was forming. This was Mars, smaller than Earth and Venus, growing more slowly because there was less material available in its region of the disk. Mars would never grow large enough to fully differentiate and maintain a molten interior for billions of years like Earth did. Its smaller size meant it would cool more quickly, solidifying sooner, ending its geological activity earlier in its history. But for now, it too was a growing ball of rock, accumulating mass, heating from impacts, slowly becoming a planet. The growth of these terrestrial worlds was not smooth or predictable. Each planet experienced impacts of all sizes, from tiny dust grains barely adding any mass to enormous collisions with planetesimals hundreds of miles across that could reshape the entire planet in a matter of hours. The largest impacts were rare but profound, and one impact in particular, which occurred perhaps 50 million years after the disk first began to collapse, would prove to be the most important event in Earth's formation. A planetesimal about the size of Mars, itself a planetary embryo that had grown large in a region near Earth's orbit, found itself on a collision course with the proto-Earth. Perhaps its orbit had been perturbed by a close pass with Venus or by the cumulative effect of many smaller gravitational interactions. Whatever the cause, this massive body, sometimes called Theia by scientists, was heading directly toward Earth at a speed of several miles per second. The collision between Theia and Earth was not a head-on crash but a glancing blow, with Theia striking Earth at an angle. The impact released more energy than any event Earth had experienced before or would experience again. The entire planet rang like a bell, its molten surface thrown into chaos. A significant portion of Theia and of Earth's mantle was vaporized and blown into space, forming a vast cloud of hot rock vapor and debris that surrounded the planet in a glowing ring. Over the following thousands of years, this ring of debris began to cool and condense and gather together. Particles stuck to each other, small accumulations grew larger, and eventually, most of the material in the ring coalesced into a single body orbiting Earth. This body became the Moon, Earth's companion, our nearest neighbor in space, forever bound to us by the gravity that resulted from this ancient catastrophic collision. The impact had other lasting effects on Earth. It tilted Earth's axis of rotation by about 23 degrees, giving our planet its seasons, its variation in climate between summer and winter. It also added angular momentum to the Earth-Moon system, speeding up Earth's rotation so that days were much shorter than they are now, perhaps just 5 or 6 hours long in the aftermath of the impact. Over billions of years, tidal forces between Earth and Moon would gradually slow Earth's rotation and push the Moon further away, but that is a story for another time. After the giant impact, Earth continued to grow, though now most of the large planetesimals had already been swept up, and the remaining collisions were with smaller bodies. The bombardment continued for hundreds of millions of years, a period called the Late Heavy Bombardment, when the inner solar system was still clearing out the last debris from planet formation. Each impact added a little more mass to Earth, a little more heat, and sometimes brought new materials that had formed in different parts of the solar system. The outer planets, the giant worlds of Jupiter and Saturn and Uranus and Neptune, were also forming during this time, though their story was different. Beyond the frost line, these planets could incorporate vast amounts of ice along with rock and metal, and they grew much larger than the terrestrial worlds. Jupiter in particular grew so large that its gravity began to dominate the outer solar system, flinging planetesimals inward toward the Sun and outward toward interstellar space, stirring up the disk, perturbing orbits, causing some of the bombardment that the inner planets experienced. But here in the inner solar system, the terrestrial planets were beginning to settle into their final configurations. The disk of gas and dust was dissipating, blown away by the solar wind and by radiation pressure from the now shining sun. Without the gas to dampen their motion, the remaining planetesimals moved on more eccentric orbits, leading to more energetic collisions, but also gradually clearing out the space between planets. The solar system was beginning to look less like a chaotic disk and more like a set of discrete worlds, each orbiting peacefully in its own zone. And on Earth, after hundreds of millions of years of bombardment and growth and chaos, the surface finally began to cool. With fewer impacts to keep heating it, with heat radiating away into space, the molten surface started to solidify, forming the first solid crust, the first true ground. This crust was thin at first, probably unstable, frequently disrupted by impacts and by volcanic activity from below, but it was the beginning of something permanent, something stable, something that would eventually support oceans and continents and life itself. Earth taking shape in the darkness. The young Earth that emerged from the violence of its formation was a world unrecognizable compared to the planet we know today. Picture, if you can, a sphere hanging in the darkness of space, glowing with its own internal heat like a coal fresh from a fire. The surface was covered by an ocean of magma, liquid rock extending around the entire planet, no solid ground anywhere, just this glowing molten sea, rippling and churning with currents driven by the heat below. Above this magma ocean hung an atmosphere, though calling it an atmosphere barely captures what it was. This was not air as you know it, not oxygen and nitrogen gently supporting life. This early atmosphere was thick and hot and toxic, filled with water vapor and carbon dioxide and methane and ammonia, gases that had been released from the rocks as they melted, gases that had been delivered by countless impacts of comets and asteroids. The atmosphere was so dense that it trapped heat like a heavy blanket, keeping the surface hot even as the planet slowly cooled. The moon hung in the sky much closer than it does today, perhaps just 15,000 miles away compared to the 240,000 miles that separate us now. It appeared enormous from Earth's surface, filling a large portion of the sky, its own face still molten and glowing from its recent formation. The tidal forces between Earth and Moon were intense at this close distance, raising enormous tides in Earth's magma ocean, bulges of molten rock that traveled around the planet following the Moon's position overhead. Time passed, measured not in days or years but in millions of years. The Earth continued to radiate heat into space, that unavoidable process of cooling that all warm objects undergo. The magma ocean began to cool from the top down, its surface losing heat to space faster than heat could be supplied from below. A thin skin of solid rock began to form on the surface, the first crust, though it was fragile and temporary. This early crust was like the skin that forms on cooling pudding, thin and easily broken. Underneath, the magma ocean still churned, and currents of molten rock would break through the crust, flooding areas with fresh lava, remelting the solid rock back into liquid. The crust would form again, and break again, and form again, this cycle repeating thousands of times as the planet gradually cooled. But with each cycle, more crust survived. The mantle beneath the magma ocean was cooling too, solidifying from the bottom up, and as it did, it could support the weight of the crust above more effectively. The solid portions of the crust began to thicken, to persist, to become permanent features. After perhaps 100 million years of cooling, the surface of Earth was finally, truly solid, covered by a thin shell of rock that floated on the still partially molten mantle below. This early crust was made primarily of basalt, a dark volcanic rock rich in iron and magnesium, similar to the rock that forms the ocean floor today. It was dense and heavy, and it would not last forever in its original form. Over time, geological processes would recycle it back into the mantle, and lighter rocks would form from its reprocessing, but for now, it was the first solid ground that Earth had ever known. As the surface cooled below the boiling point of water, something remarkable became possible. The water vapor that had filled the atmosphere, enormous quantities of it delivered by countless comets and water-rich asteroids during the formation process, could finally condense. It began to rain, the first rain in Earth's history, and this rain fell upon the hot rocks of the newborn crust. At first, the rain never reached the ground. The rocks were still so hot that water would evaporate instantly upon contact, flashing back to steam, rising to cool and condense and fall again. But gradually, relentlessly, the rain cooled the rocks, and eventually the rocks cooled enough that water could remain liquid on the surface. When that threshold was crossed, the rain did not stop. It rained for thousands of years, perhaps millions of years, an endless deluge of water falling from the sky, accumulating on the surface, finding the low places and pooling there. The first oceans began to form. At first they were small and scattered, countless pools and lakes filling the depressions in the irregular basalt crust. But water flows downhill, seeking the lowest level, and gradually these pools merged and connected, flowing together, creating larger and larger bodies of water. The low regions of the crust, the deepest basins, filled with water hundreds or thousands of feet deep. The high regions remained as land, dark volcanic islands rising from the growing seas. These early oceans were not the clear blue waters you might imagine. They were probably greenish or gray, filled with dissolved minerals that the rain had leached from the rocks, chemicals like iron and sulfur and chlorine. The water was hot, perhaps close to boiling in some places where volcanic vents released heat from below, cooler in other places where the crust had solidified more completely. And the water was slightly acidic, because the atmosphere still contained vast amounts of carbon dioxide, which dissolved in the water to form carbonic acid. Above the oceans, the sky was not blue. The atmosphere was still thick with carbon dioxide and water vapor, and these gases scattered sunlight differently than our current atmosphere does. The sky was probably orange or reddish, and the sun appeared dimmer through the hazy air, though it was actually younger and slightly less bright than it is today. Storms raged continuously across this early Earth, driven by the temperature contrasts between the hot surface and the cooler upper atmosphere, by the rapid rotation of the planet, and by the tidal effects of the nearby moon. Lightning flashed constantly through these storms, billions of lightning bolts every day, each one releasing energy that could break apart the simple molecules in the atmosphere and allow them to recombine in new configurations. In the oceans, underwater volcanoes erupted frequently, creating new crust, releasing gases and heat and minerals into the water. The planet was alive with energy, with motion, with change, though no living thing existed yet to witness it. The crust was not static during this period. It was broken into pieces, plates that floated on the partially molten mantle below, and these plates moved, pushed by currents in the mantle. Where plates moved apart, magma would well up from below, creating new crust, forming underwater volcanic ridges. Where plates collided, one would be forced down beneath the other, sinking back into the mantle to be remelted, recycled, its minerals incorporated into new rock that would eventually rise again. This process, called plate tectonics, was crucial for creating the variety of rock types we see on Earth today. The basaltic crust that covered the early Earth would be subducted into the mantle, partially melted, and the lightest components of that melted rock would rise back to the surface, forming new rock that was less dense, more silicon-rich. Over millions of years, this process created granite and other continental rocks, lighter than basalt, less likely to be subducted, and therefore accumulating at the surface to form the first proto-continents. These early landmasses were nothing like the continents today. They were small, perhaps just a few hundred miles across, scattered randomly across the planet's surface. They were barren, lifeless expanses of dark rock under that orange sky, waves crashing against their shores, rain falling constantly, lightning flashing. But they were stable, permanent, growing slowly as more light rock was added to them through continued volcanism and differentiation. Earth's atmosphere was also changing during this period. The carbon dioxide that dominated the early atmosphere began to dissolve in the oceans, and chemical reactions with the rocks removed it from the water, locking it away in carbonate minerals. This process slowly reduced the greenhouse effect that had kept the early Earth so hot, allowing the planet to cool further. The water vapor also decreased as more water condensed to form oceans, and the atmosphere became thinner, less oppressive, more transparent to sunlight. The moon, meanwhile, was receding, pushed away by tidal forces at a rate of about 1.5 inches per year. As it moved further from Earth, its influence on tides diminished, and Earth's rotation gradually slowed, days becoming longer, though this process would take billions of years to reach the 24-hour day we experience now. By the time Earth was perhaps 600 million years old, it had transformed from a glowing ball of molten rock into a world with oceans and land and a relatively thin atmosphere. The surface temperature had dropped to perhaps 160 or 180 degrees Fahrenheit, still hot compared to today, but within the range where certain chemical reactions could occur, certain molecules could form, certain processes could begin that would not have been possible in the earlier, hotter conditions. The stage was set. The planet had solid ground, liquid water, an atmosphere of gases, energy from the sun and from internal heat and from lightning and from impacts. All the ingredients were present, all the conditions met, for the next great chapter in the story of Earth. The planet was ready, though it did not know it, could not know it, was not conscious or aware in any way. It was just a world, hanging in space, cooling and changing and waiting. Waiting for something impossible, something that should not happen but somehow does. Waiting for life. The dust that carried water and life's building blocks. To understand how life began, we must return for a moment to the space between stars, to the cold clouds of gas and dust that exist everywhere in our galaxy. These clouds are not just made of rock and ice. Within them, chemistry is happening, slow chemistry, molecules forming and breaking apart over millions of years, but chemistry nonetheless. And some of the molecules that form there are surprisingly complex, surprisingly similar to the molecules that living things are made of. In the coldest regions of interstellar space, where temperatures hover just a few degrees above absolute zero, simple molecules can stick to the surfaces of dust grains and react with each other. A carbon atom might meet an oxygen atom and form carbon monoxide. A nitrogen atom might encounter hydrogen atoms and form ammonia. Water forms easily, just oxygen and hydrogen finding each other on a dust grain surface and bonding together. But more complex molecules form as well. Scientists using radio telescopes have detected more than 200 different molecules in interstellar space, and many of them are organic molecules, molecules based on carbon, the same element that forms the backbone of all living things. There are simple sugars in space, dissolved in the ice that coats dust grains. There are amino acids, the building blocks of proteins, forming through reactions driven by ultraviolet light from distant stars. There are fatty acids that could form cell membranes, and nitrogen compounds called nucleobases that are components of DNA and RNA. These molecules are not life. They are not alive. They cannot reproduce or evolve or respond to their environment. They are just molecules, complex molecules, but still just chemistry. However, they are the raw materials that life would need, the precursors, the ingredients. And they exist naturally, formed by ordinary chemical processes in the ordinary conditions of interstellar space. Life's building blocks are not rare or special or difficult to make. They are common, ubiquitous, floating throughout the galaxy on tiny grains of dust. When the solar nebula collapsed and formed the disk that would become our solar system, it incorporated these interstellar dust grains, along with all the complex molecules that coated their surfaces. As planetesimals formed and grew, these molecules were trapped inside them, frozen into the ice and rock that made up these early bodies. And when planetesimals collided with the growing Earth, they delivered their cargo of complex molecules to our planet's surface. The planetesimals that formed in the outer solar system, beyond the frost line, were particularly rich in these organic molecules because they contained large amounts of ice, and the molecules were preserved in that ice, protected from heat and radiation. These outer planetesimals became comets, icy bodies that spend most of their time in the cold outer reaches of the solar system but occasionally fall inward toward the sun, their orbits perturbed by gravitational interactions with the giant planets. During Earth's formation and for hundreds of millions of years afterward, comets frequently struck our planet. Each impact delivered tons of water, ice, and organic molecules, adding to Earth's growing oceans and to the inventory of complex chemicals dissolved in those oceans. Asteroids, too, particularly those from the outer parts of the asteroid belt, contained water and organic compounds, and they also bombarded Earth, contributing their materials to our planet. Scientists estimate that millions or even billions of tons of organic molecules were delivered to Earth this way, not all at once but gradually, over millions of years of bombardment. These molecules accumulated in the oceans, dissolved in the water, concentrated in certain areas where evaporation occurred or where waves crashed against rocky shores. The early oceans became a thin soup of organic chemicals, not life but the ingredients for life, waiting to be assembled into something more complex. The water itself was crucial, of course. Life as we know it cannot exist without liquid water. Water is an amazing solvent, capable of dissolving more substances than any other liquid, and this property allows molecules to move and interact and react with each other. Water is stable over a wide range of temperatures, remaining liquid from 32 degrees to 212 degrees Fahrenheit at normal pressure, and this stability provides a consistent environment for chemistry. And water molecules have a slight electrical polarity that makes them interact in interesting ways with other molecules, helping to organize and structure more complex assemblies. The Earth's oceans provided not just water but also concentration mechanisms. In shallow pools that occasionally dried out in the sun, dissolved molecules would be left behind in higher concentrations as the water evaporated. Near underwater volcanic vents, where hot mineral-rich water emerged from cracks in the seafloor, minerals would precipitate out as the hot water mixed with cold seawater, and organic molecules would stick to these mineral surfaces, bringing different types of molecules into close proximity where they could react. Energy was also abundant on early Earth. Sunlight bathed the planet's surface, and ultraviolet light, which was stronger then because there was no ozone layer to absorb it, could drive chemical reactions that would not happen otherwise. Lightning provided intense bursts of energy, perhaps 100 million lightning strikes per day, each one capable of breaking molecular bonds and creating reactive fragments that could recombine in new ways. Heat from volcanic vents and from impacts provided yet another energy source, and certain chemical reactions at the rock-water interface could release energy that could drive other reactions. In the laboratory, scientists have recreated some of the conditions of early Earth and shown that complex organic molecules form readily. The famous Miller-Urey experiment of 1953 took simple gases like methane, ammonia, and hydrogen, subjected them to electrical sparks to simulate lightning, and found that amino acids formed spontaneously. More recent experiments have shown that other important biological molecules, including the nucleobases that make up DNA and RNA, can form under similar conditions. But there is a vast gulf between having organic molecules and having life. A collection of amino acids is not a protein. A mixture of nucleobases is not DNA. These molecules had to somehow organize themselves into functional structures, had to find ways to catalyze reactions, to store information, to reproduce. How this happened is still one of the deepest mysteries in science, though researchers have uncovered many clues. One important insight is that certain molecules can catalyze reactions, meaning they help reactions happen faster without being consumed themselves. Some RNA molecules, for example, can catalyze chemical reactions, including reactions that help create more RNA. This suggests a possible early form of life based on RNA rather than DNA and proteins, a so-called RNA world where RNA served as both the information storage system and the catalytic machinery. Another insight is that lipid molecules, the fatty compounds that form cell membranes, can spontaneously organize themselves into hollow spheres called vesicles when they are placed in water. These vesicles create a boundary, an inside and an outside, and if there are RNA molecules or other interesting molecules trapped inside a vesicle when it forms, they are now contained in a primitive cell-like structure, protected from the environment, able to react with each other without being diluted into the vast ocean. Perhaps life began when RNA-like molecules that could catalyze their own replication became enclosed in lipid vesicles, creating the first protocells. These protocells could absorb molecules from their environment, use them to make more RNA and more lipids, and eventually divide when they grew too large, creating two cells from one. This would be replication, inheritance, evolution, all the hallmarks of life, though in an extremely simple form. Or perhaps life began in a completely different way, in environments we haven't even considered, through processes we don't yet understand. The truth is, we don't know exactly how life started. We know it happened because we are here, living proof that the journey from dust to life is possible. But the precise pathway, the exact sequence of events, remains hidden in the deep past, perhaps 4 billion years ago, perhaps earlier, in an ocean we will never see, under a sky we can never visit. What we do know is that the dust from space carried the ingredients. The comets and asteroids that bombarded early Earth were not just destructive forces but also creative ones, delivery systems bringing the building blocks of life from the cold vastness of space to the surface of our warm, wet planet. Every amino acid in your body, every nucleobase in your DNA, was once part of a dust grain floating in interstellar space, was once locked in ice in a distant comet, was once delivered to Earth by a violent impact that lit up the sky. The connection between you and that ancient dust is direct and undeniable. The carbon atoms that form the backbone of every organic molecule in your body were created in stars, ejected into space, incorporated into dust grains, delivered to Earth, assembled into simple molecules, then more complex molecules, then cells, then organisms, then eventually, billions of years later, into you. You are made of processed stardust, reorganized and refined through countless generations, but stardust nonetheless. This is not poetry or metaphor but literal truth, verified by physics and chemistry and biology. From stardust to living cells. The early oceans of Earth held the ingredients for life, but ingredients are not a recipe. For hundreds of millions of years, organic molecules accumulated in the water, concentrated in certain areas, mixed and reacted and broke apart and form began. Chemistry was happening, endless chemistry, trillions upon trillions of reactions occurring simultaneously in different locations, most of them leading nowhere, producing nothing of significance, just molecules shuffling themselves randomly like cards in a cosmic deck. But chemistry, when given enough time and enough opportunities, can stumble upon combinations that are special, configurations of molecules that have interesting properties. Perhaps in a tidal pool somewhere, warmed by the sun, stirred by waves, a particular arrangement of RNA-like molecules formed that could catalyze its own replication. This molecule could use the nucleobases floating in the water around it to make a copy of itself, a complementary strand that could then serve as a template to make another copy of the original. This replication would not be perfect. Mistakes would happen, nucleobases would occasionally be added incorrectly, and the copy would be slightly different from the original. Most of these mistakes would be harmful, creating molecules that could not replicate efficiently or at all. But occasionally, rarely, a mistake might create a molecule that was better at replicating, that could gather resources more efficiently, that could survive in a wider range of conditions. This is evolution at its most fundamental level. Replication, variation, selection. Molecules that could replicate would become more numerous. Molecules that replicated faster or more accurately would outcompete those that replicated more slowly. Molecules that could survive in harsher conditions would persist when others failed. Over millions of years, this process would drive the development of increasingly sophisticated molecular systems. The protocells we imagined earlier, vesicles of lipids containing replicating RNA, would also evolve. Vesicles that could grow and divide efficiently would proliferate. Vesicles that could maintain their internal environment, controlling what molecules entered and exited, would survive better than those that could not. Random combinations of molecules within vesicles would occasionally produce systems that worked well together, catalytic networks where one molecule's product was another molecule's substrate, creating cycles of reactions that reinforced each other. One particularly important development was the evolution of molecules that could store information more reliably than RNA. DNA, which is chemically similar to RNA but has some key differences, is more stable and can store information with fewer errors. The transition from an RNA-based genetic system to a DNA-based one allowed protocells to maintain larger genomes, encoding more information, supporting more complex molecular machinery. Another crucial development was the evolution of proteins. While RNA can catalyze reactions, proteins are far more versatile catalysts, able to fold into an enormous variety of shapes and perform an enormous variety of functions. The development of ribosomes, molecular machines that could translate information stored in RNA into proteins, was a major leap forward in complexity. Now genetic information in DNA could be transcribed to RNA, which could then be translated to proteins, creating the central dogma of molecular biology that operates in every living cell today. These early cells, if we can call them that, were simple beyond imagining compared to modern cells. They had no nucleus, no organelles, no sophisticated internal structure. They were just bags of molecules, self-replicating bags whose contents could occasionally produce more bags. But they were alive. They could reproduce, they could evolve, they could metabolize, taking in molecules from their environment and using them for energy and construction. They were the first organisms, the ancestors of every living thing that exists today. These first cells probably obtained energy through fermentation, breaking down simple organic molecules without oxygen, releasing a small amount of energy in the process. The oceans still contained organic molecules delivered from space or created by lightning and volcanic activity, and the early cells could feed on this organic matter, though it was not an infinite resource. Eventually, competition for these molecules would drive the evolution of new metabolic strategies. The most important of these new strategies was photosynthesis, the ability to use sunlight directly to create organic molecules from carbon dioxide and water. The evolution of photosynthesis, probably about 3 billion years ago, was revolutionary. For the first time, life could create its own food rather than depending on the limited supply of organic molecules from non-biological sources. Cells that could photosynthesize had access to essentially unlimited energy from the sun and unlimited raw materials from the carbon dioxide in the atmosphere and the water all around them. The earliest photosynthetic organisms probably did not produce oxygen as a byproduct. They used different chemical reactions that released other products like sulfur instead. But eventually, perhaps 2.5 billion years ago, certain bacteria evolved a form of photosynthesis that split water molecules to obtain hydrogen, releasing oxygen as waste. This oxygenic photosynthesis would change everything. At first, the oxygen released by these bacteria was absorbed by minerals in the ocean and rocks on land, particularly iron, which readily reacts with oxygen to form rust. For hundreds of millions of years, the oxygen was consumed by these geological sinks and little accumulated in the atmosphere. But eventually, the supply of easily oxidized minerals was exhausted, and oxygen began to accumulate in the ocean and atmosphere. This accumulation of oxygen, called the Great Oxidation Event, was probably catastrophic for most life at the time. Oxygen is reactive, toxic to organisms that evolved in an oxygen-free world. It can damage the delicate molecules that life is made of. Many species probably went extinct, unable to cope with this new, poisonous gas. But some organisms evolved defenses against oxygen, and some even learned to use it to their advantage. Oxygen allows for aerobic respiration, a way of extracting energy from organic molecules that is far more efficient than fermentation. Organisms that could breathe oxygen could obtain much more energy from the same amount of food, and this energy surplus enabled the evolution of larger, more complex organisms. The rise of oxygen was a necessary precondition for the development of multicellular life, of animals, of plants, of everything visible that inhabits Earth today. But we're getting ahead of the story. For now, we are still in the early days, when life consisted of single-celled organisms, bacteria and archaea, simple yet successful, spreading throughout the oceans, adapting to every available environment, evolving, diversifying, laying the foundation for all the complexity that would come later. These cells were the culmination of a process that began with dust in space, continued through the formation of planets, and resulted in something completely new, something that the universe had never seen before in this corner of space. Not just matter, not just chemistry, but life. And every cell in your body is a descendant of those first cells. Your cells use the same genetic code, the same basic molecular machinery, the same fundamental processes as bacteria that have existed for billions of years. You are not separate from that ancient story, but a continuation of it, a new chapter in a narrative that began in Stardust and continues in you. The atoms in your body were once in those first cells, have been recycled through countless organisms over billions of years, and are now temporarily assembled into the form of you, before they are recycled again into whatever comes next. The cosmic dust still falling today. The story of dust delivering materials to Earth is not just ancient history. It is happening right now, tonight, as you lie here. At this very moment, tiny particles of dust from space are drifting down through the atmosphere, adding their small mass to our planet, connecting us to the cosmos in a gentle, ongoing process that has never stopped. Scientists estimate that Earth gains about 40,000 tons of space dust each year. That sounds like a lot, and in absolute terms it is, but spread across the entire surface of our planet, it amounts to just a few specks of dust per square foot per year. You would never notice it accumulating. It mixes with terrestrial dust, with soil, with sediment, becoming indistinguishable from the Earth materials that surround it. But it is there, a constant reminder that our planet is not isolated from space but connected to it, part of it, receiving a small steady supply of extraterrestrial matter. This space dust comes from several sources. Some of it is debris from asteroids, tiny fragments created when asteroids collide with each other in the asteroid belt between Mars and Jupiter. These collisions are rare for any individual asteroid, but there are so many asteroids that collisions happen somewhere in the belt fairly regularly, and each collision creates clouds of dust that gradually spread throughout the inner solar system. Some of this dust eventually encounters Earth, captured by our planet's gravity and atmosphere. Some of the dust comes from comets. As a comet approaches the Sun, the ice on its surface begins to vaporize, and this vaporization carries dust particles away from the comet's nucleus, leaving a trail of debris along the comet's orbit. When Earth passes through one of these debris trails, we experience a meteor shower as thousands of dust particles enter the atmosphere simultaneously, burning up and creating streaks of light across the night sky. Most of these particles burn completely, but the smallest ones can survive the journey to the ground. And some of the dust is truly interstellar, particles that formed in the space between stars and happen to be passing through our solar system on their way to somewhere else. These interstellar dust grains are rarer than the asteroid and comet dust, but they have been detected, caught in collectors mounted on spacecraft and even in Earth's upper atmosphere. They offer a direct sample of material from beyond our solar system, a physical connection to the rest of the galaxy. When space dust enters Earth's atmosphere, moving at speeds of perhaps 7 to 45 miles per second, it experiences intense friction with the air molecules. This friction heats the particle, and if the particle is large enough and fast enough, it will heat to the point where it glows, creating a meteor, a shooting star, visible from the ground. Most meteors are caused by particles no larger than a grain of sand, yet they create brilliant streaks of light as they vaporize 50 or 60 miles above the surface. The smallest dust particles, however, those less than 1/10 of a millimeter across, don't generate enough heat to vaporize completely. They are slowed by the atmosphere but survive the journey, drifting down slowly, taking days or weeks to settle from the upper atmosphere to the ground. These particles, called micrometeorites, can be found anywhere on Earth, though they are easiest to collect in places where there is little terrestrial dust to contaminate the samples, like the ice of Antarctica or the ocean floor. Scientists who study these micrometeorites have learned remarkable things from them. Many contain complex organic molecules, the same kinds of molecules that were delivered to early Earth billions of years ago. Some contain tiny crystals of silicate minerals that formed around other stars, before our solar system even existed. These are pre-solar grains, material that is older than the Sun, that has traveled across light years of space and now rests on our planet, waiting to be discovered. The organic molecules in micrometeorites are similar to those found in certain meteorites that have fallen to Earth, larger pieces of asteroids and comets that survive atmospheric entry because of their size. These meteorites have been studied extensively, and they contain amino acids, nucleobases, sugars, lipids, all the categories of molecules that life uses. The ratio of different isotopes in these molecules proves that they formed in space, not on Earth, confirming that space is indeed a factory for organic chemistry. This ongoing delivery of organic molecules and water from space means that Earth is continually receiving a small resupply of the raw materials for life. The amount is tiny compared to what was delivered during the heavy bombardment of early Earth, but it is not zero. Every year, tons of organic compounds drift down from space, adding to the inventory of carbon on our planet, perhaps occasionally introducing new molecular varieties that Earth's chemistry had not previously produced. There is even speculation that life itself might occasionally be delivered from space, though this is highly controversial. Certain bacteria on Earth are extremely hardy, capable of surviving in the vacuum of space, in intense radiation, in freezing cold. If such bacteria were somehow ejected from Earth, perhaps by a large asteroid impact that launched rocks into space, could they survive the journey to another planet and seed life there? This idea, called panspermia, is an old one, and while most scientists think it is unlikely to be how life originated in the first place, it is not impossible that hardy microorganisms could survive interplanetary journeys. Even if bacteria don't travel between planets, the organic molecules certainly do. Every planet in the solar system receives its share of cometary dust and asteroid debris. Mars receives micrometeorites, as do Venus and Mercury, even the moons of Jupiter and Saturn. The organic chemistry of space is delivered everywhere, to every solid surface, a gift from the cosmos that does not discriminate by location. Looking at the space dust falling today connects us to the processes that formed our planet and created life. The same mechanisms are operating now that operated 4 billion years ago. Dust forms in space, gathers into larger bodies, some bodies collide with planets, delivering their materials. The rate of delivery is much lower now than it was in the early solar system because most of the material has already been swept up, but the process continues. And this means that planet formation itself is not entirely finished. Earth is still accumulating mass, still growing, albeit at an incredibly slow rate. If you could weigh the planet with perfect precision and then weigh it again a year later, you would find it has gained those 40,000 tons, a completely negligible amount compared to Earth's total mass of 6.5 billion tons, but not zero. We are still, very slowly, still being built by cosmic dust. This ongoing connection to space, this gentle rain of dust particles, is a comfort in a way. It reminds us that Earth is not a closed system, not isolated, not alone. We are part of the solar system, and the solar system is part of the galaxy, and the galaxy is part of the universe. The boundaries we perceive between Earth and space, between terrestrial and extraterrestrial, are permeable, arbitrary, illusions created by our limited perspective. Material flows across these boundaries constantly, has always flowed, will always flow, connecting everything to everything else in this vast cosmic web. You are made of ancient starlight. Now we come to the end of our journey, though calling it an end is not quite right because this story has no ending, only transformations, only continuations. Let us rest here for a while and consider what we have learned, what it means for you personally, lying here, breathing slowly, part of this ancient story. Every atom in your body has a history that stretches back billions of years. Take the carbon atom that is part of a DNA molecule in one of your cells right now. This atom was created perhaps 7 or 8 billion years ago inside a star much larger than our Sun. That star fused hydrogen into helium for millions of years, then fused helium into carbon, building up the element atom by atom in its core through nuclear reactions that released tremendous energy. When that star exhausted its fuel and exploded as a supernova, our carbon atom was thrown into space along with countless others, part of an expanding cloud of star material that would eventually join an interstellar dust cloud. For millions of years, this carbon atom drifted through space, perhaps coating the surface of a dust grain, perhaps part of a simple molecule like carbon monoxide. It was present in the cloud that collapsed to form our solar system, was incorporated into a comet in the outer regions of the disk, spent billions of years frozen in that comet, and was eventually delivered to Earth when the comet impacted our planet, perhaps 3.5 billion years ago. On Earth, the carbon atom dissolved in the ocean, was taken up by one of the first photosynthetic bacteria, was incorporated into an organic molecule in that bacterium's body, was released when the bacterium died and broke down, was taken up again by another organism, then another, then another. Over billions of years, this single carbon atom has been part of countless organisms, perhaps bacteria, perhaps algae, perhaps plants, perhaps animals. It has been part of the bodies of creatures that lived in ancient seas, creatures that crawled onto land, creatures that evolved and diversified and went extinct. Perhaps it was part of a dinosaur's body once, incorporated into a molecule of protein in a muscle cell, used for millions of years as that dinosaur grew and lived and eventually died. The carbon atom would have been released back into the environment, perhaps absorbed by a plant, then eaten by another animal, then another, cycling through the biosphere again and again. Perhaps it spent time as part of the wood in a tree, then was released as carbon dioxide when the tree burned in a forest fire, then was absorbed by another plant, then eaten by an animal, perhaps a mammal, perhaps one of your ancestors. And eventually, through a path we could never trace in detail, this carbon atom ended up in food that you ate, was absorbed by your digestive system, was transported in your bloodstream, was incorporated into a DNA molecule during cell division, and now resides in you, part of the genetic material that makes you who you are. This atom has traveled from the core of a star to the interior of your cells, a journey across space and time that connects you directly to the cosmos. This is true not just for one carbon atom but for every atom in your body. The oxygen atoms in the water that makes up most of your mass were also created in stars, forged in fusion reactions and dispersed into space by supernovae. The nitrogen atoms in your proteins and DNA, the calcium atoms in your bones, the iron atoms in your blood that carry oxygen to your cells, all of them were created in stars, all of them have traveled through space, all of them have been part of the Earth for billions of years, cycling through countless organisms before becoming part of you. You are not separate from this story. You are not an observer looking at it from outside. You are made of the same substance that makes up stars and planets and dust clouds. The atoms in your body are the same atoms that have existed since the early universe, that have been part of countless structures, countless forms, countless beings. You are a temporary configuration of ancient atoms, a pattern that these atoms are forming right now, in this moment, before they move on to form something else. This is not diminishing or reductive. It does not make you less special or less significant. Rather, it connects you to everything else in the universe, makes you part of the grand story of matter and energy and transformation that has been unfolding for 13.8 billion years. You are the universe experiencing itself, matter that has become complex enough to be conscious, to think, to wonder, to ask questions about its own origins. The dust that formed planets did not stop being dust when it became part of planets. It became organized dust, structured dust, dust that could hold heat and have weather and develop chemistry. And when some of that dust became part of living cells, it did not stop being dust. It became incredibly organized dust, dust that could reproduce and evolve and adapt. And when some of that living dust became complex enough to think, it did not stop being dust. It became conscious dust, aware dust, dust that could ponder its own existence. This is what you are. Stardust, shaped by 4 billion years of evolution into a form that can think and feel and dream. Every thought you think is atoms interacting, molecules changing, electrons moving, all of it dust, all of it ancient, all of it connected to the beginning of everything. And when you die someday, far in the future, the atoms that currently make up your body will be released back into the world. They will become part of soil, part of air, part of water. They will be taken up by plants and bacteria and animals. They will continue the journey, continue cycling through the biosphere and perhaps eventually back into space when the sun dies and the earth is destroyed and the atoms are scattered once again into the galaxy. But for now, right now, they are you. These ancient atoms that have seen so much, that have been so many things, are currently assembled into the pattern that is you, experiencing this moment, breathing this breath, thinking these thoughts. It is a privilege to exist, a temporary gift of organization and consciousness in a universe that is mostly empty space and mindless matter. So as you drift towards sleep tonight, comfortable and warm and safe, remember your connection to the cosmos. Remember that you are made of stars, literally and physically made of the same substance that stars are made of, recycled and reorganized but fundamentally the same. Remember that the dust that fell from space to form the earth is the dust that became you, that the atoms in your body are older than mountains, older than continents, older than the planet itself. You are a way for the cosmos to know itself, as Carl Sagan said. You are the universe made conscious, matter that can appreciate its own existence, can feel gratitude for the improbable journey that led from dust and space to thoughts and a mind. Rest now, knowing that you are part of something vast and ancient and ongoing, knowing that your connection to the stars is not metaphorical but real, knowing that every atom in you has traveled an unimaginable distance to be here, now, in you. Sleep well, child of stardust. Sleep well, fragment of ancient stars. Sleep well, knowing that you are home, here on this planet made of dust, spinning through space under the light of the sun that was born from the same cloud that made you, surrounded by the same elements that filled the universe billions of years ago, at peace with your place in the cosmos, at rest in the knowledge that you are exactly where you are meant to be, made of exactly what you are meant to be made of, connected to everything, part of everything, held gently by the same forces that hold galaxies together, the same forces that brought dust together to form worlds and life in you. Rest now. The dust is still falling, gently, silently, adding to the earth, continuing the process that has never stopped. The stars are still shining, fusing elements, creating new atoms that will someday be part of new worlds, new life, new stories. The universe continues its ancient dance of creation and destruction and transformation, and you are part of that dance, have always been part of it, will always be part of it, even after the pattern that is you dissolves and the atoms move on to new configurations. But tonight, in this moment, you are here. You are conscious. You are aware. You are made of stardust, and you know you are made of stardust, and that knowing is itself a remarkable thing, a wonder, a gift. Rest in that wonder. Let it surround you like a warm blanket. Let the vastness of cosmic time and space hold you gently as you drift into sleep, knowing that you are safe, you are connected, you are part of the great story of dust becoming everything, including you.